So I have the matrix A, 2, 3, 2, 3, 2, 2, 2, 2, 3. Okay, and I want to do a QR decomposition of it using again the Householder transformation. So I will again find first my vector u, which is defined as x minus x prime, where x is the first column vector of A, so this 2, 3, 2, and x prime is the norm of this this vector x, so the square root of 2 squared plus 3 squared plus 2 squared. So the square root of 17, okay? 2 squared is 4, 2 squared plus 2 squared is 8, okay, so 4 plus 4, and 3 squared is 9, so 9 plus 4 plus 4, so 9 plus 8, so 9 plus 8 is 17, so the square root of 17. So our vector x prime is the square root of 17 and 0, 0, okay, 0 elsewhere. Yes, the square root of 17 is in the first place. Okay, so now my Householder transformation is given as the identity matrix minus 2 times u transpose over u transpose u. Okay, remember that this u transpose u in the denominator is simply the dot product. Okay, remember that you can write the dot product in matrix form as u transpose u. Okay, this is simply this thing, if I remember well. This is simply the dot product, okay? Because we need to normalize this vector u and this vector u transpose, okay? Because we want the unit vector, remember that. Yes, so now we plug in everything. Inside the formula we have found our vector u. The vector u transpose is simply, well, you transpose it, basically, that's just what we did. So you transpose it, I think you know what I mean. Simply transposing a vector is like, if it is like that, you put it like that, okay, and the inverse is also true if it's first like that. Sorry, if it's first like that, then you transpose it by putting it like that. Okay, I hope this is clear. So you plug in everything, so you have your vector u, which is, as I said, is this this vector x minus vector x prime. So this is 2 minus square root of 17. Okay, this 2 here minus this square root of 17, 3 minus 0, so simply 3, and 2 minus 0, so simply 2. And here we transpose it, so 2 minus square root of 17, 3, 2. And in the denominator, again, this is simply, we simply take the dot product of the vector u itself, so we square each component and add the total, so 2 minus square root of 17 squared here, plus 3 squared, plus 2 squared, okay? This is simply the dot product, okay? And so yeah, don't forget to have to put this 2 here in front of it. You need to multiply this whole result here by 2, and also the negative sign here and the identity matrix, of course, in the corresponding dimensions, okay? Here we are in 3 dimensions, so the identity matrix would be a 3 by 3 matrix. If we would be in 5 dimensions, the first time the identity matrix would be in it would be a 5 by 5 matrix, okay? Of course, after each time you only consider the submatrix of A, then the submatrix, and so each time the dimensions are lower. Don't forget that. Yes, so if you compute everything, you can plug that into a calculator, or if you are motivated, you can do it by hand, but I think this is near to impossible, but you can try it if you want. You should get this result here. Okay, so 0.49, 0.73, 0.49, 0.73, 0.49, negative 0.03, negative 0.69, negative 0.69, 0.54, okay? And so that is our first Householder transformation. Let's call it H sub 1, okay? This is a 1 here, because this is our first transformation that we will apply to A. So if you apply it to A, we get this result here. Get this result here. So as expected, the first column vector only has now zeros, except for the first component, which is now the norm of the old vector. Okay, the norm of this vector 2, 3, 2. And yeah, the other components are 0 as expected. And the other results are, just for information, 3.88, sorry, 3.88, 3.88, 0.76, negative 0.66, 1.17, and 1.23, okay? And yeah, so this is our result. Let's call it A sub 1, okay? Yes, so now we will only consider this submatrix here. So this 0.76, negative 0.66, 1.17 and 1.23. Okay, so this submatrix here. And let's call it A sub 1, comma 2 by 2 submatrix. Okay, this is a 2 by 2 submatrix. Yeah, you can call it whatever you want. I just called it A sub 1 because this is the first first matrix A after a transformation, and comma 2 by 2 submatrix. Okay, because this is the 2 by 2 submatrix that we consider. Okay. So now remember, we will find again our vector u, but this time inside the submatrix, very important. So the vector x will be the first column vector of this submatrix. So this vector here, so 0.76 and 1.17. Okay, don't forget that inside the submatrix, and our vector x prime will again be the norm of this first column vector. Okay. So the norm, so the square root of 0.76 squared plus 1.17 squared, okay. And the other components will be 0, okay. Here, okay, 0, okay. Like here we are in a 2 by 2 submatrix. Here we have the 3 by 3 matrix. So obviously we have 3 components. Here we have only 2 because we are as in a 2 by 2 submatrix. So we only have one other component that is 0, not 2, because as said here we were in 3 dimensions. Here we are only in 2 dimensions. Okay. So now we can find the vector u again, which is x minus x prime. So this column vector minus this x prime here. So we get again 0.76 minus square root of 0.76 squared plus 1.17 squared. Okay. And 1.17. Okay, that doesn't change because I said you have 0 here, so we subtract 0 from 1.17, so we subtract nothing. Okay, so that is our vector u again. So now we have our vector u again, so we can plug in everything into our formula. So our second Hausdorff transformations in 2 by 2 dimensions, so considering now only this submatrix, is the identity matrix. So here in 2 dimensions, okay, a 2 by 2 identity matrix, minus 2 times this vector u transpose over u transpose u. Again, this u transpose u in the denominator is simply the dot product, okay. Yes, and this u transpose is simply a matrix multiplication, okay, with the vector u and its transpose. And also, I didn't say it, but this vector u, if you calculate it, if you plug it into a calculator, instead of writing 0.76 minus square root of 0.76 squared plus 1.17 squared, that gives simply negative 0.64 if you plug that into a calculator, okay, negative 0.64. And the 1.17 doesn't change, okay. So yes, we plug in everything inside this formula, and again, you can do it by hand if you're motivated. Otherwise, plug it into a calculator. That is what I did, and you should get 0.54, 0.84, 0.84, and negative 0.54. Okay. So this is our second Hausdorff transformation, but considering only the submatrix. So for now, only a 2 by 2 matrix. So now that we can multiply it with A, we need to have the same number of dimensions. So what we do, as in the other videos, is we plug in our 2 by 2 Hausdorff transformations that we found here inside, and we fill everything else with zeros outside the diagonal and ones inside the diagonal. Okay, so here A is originally a 3 by 3 matrix, so we only need to do it once. So we put in zeros here and the 1 here in the diagonal. But if A would originally be a 4 by 4 matrix, and that we are already considering the submatrix, so the second submatrix, because for a 4 by 4 matrix, the first submatrix would be a 3 by 3 matrix. Okay, would be a 3 by 3 matrix, like 4 by 4. It is the first submatrix would be a 3 by 3 matrix. So the second one would be a 2 by 2 matrix. Okay, and so in this case you need to put two ones in the diagonals and lots of zeros, of course. Okay, so here you would put it your 2 by 2 householder submatrix. Okay, could write it a bit more like that. Okay, so so always you put in your householder transformations with the dimensions of the submatrix, then you fill in the rest with ones in the diagonal and 0 elsewhere. Okay, and so if you do that, we get this 1 0 0 0 0, and this result here we plug in here. So again, the same thing as before. So it's 0.54, 0.84, 0.84, and negative 0.54. And so if we apply it to a sub 1, which was the result of h sub 1 times a, okay, so which was the result of our first householder transformations, this h sub 2 times a sub 1 is basically simply h sub 2 times h sub 1 times a, okay, that this h sub 1 times a is our a sub 1 that we defined here. This is simply the result of the first transformations that we did before. Okay, so if you do that again, so the things outside the submatrix that we considered here didn't change. Okay, so we still have square root of 17, 0, 0, 3.88, 3.88. But inside the submatrix, as expected, we have a 0 here, and this first element of the first column vector of this submatrix is now the norm of the old vector. So this 1.39 here, this is 1.49, is the norm of this old vector 0.76 and 1.17. Okay. Yes. And here we have 0.68 and negative 1.22, just for information. Okay, great. So that is now our upper triangle matrix R. Okay, we have zeros below the diagonal. Okay, here we have 0, here we have 0, here we have 0. Again, you can have 0 above the diagonal, but that doesn't need to be the case. But below the diagonal, you always need to have zeros. Above you can, but that just happens. That's not the you don't need to have zeros above the diagonal, just below it. Yeah, and so again, now remember, A is equal to QR, Q transpose A is equal to R, as usual. I think you saw that enough. So Q transpose is equal to H2 times H1, okay? Because we know that here we applied H1 and H2 to A, and we got the upper triangle matrix R, and we know that Q transpose A is equal to R, because, remember that Q is orthogonal, so its inverse is its transpose, and so we know that Q transpose is equal to H2 times H1, and so that Q is equal to H2 times H1 transposed, which is simply equal to H1 transposed times H2 transposed, according to the rules. Okay, remember that the transpose of A times B. A times B, if we take the transpose of that, is equal to B transpose times A transpose. Okay, so that's the same thing here. So Q is equal to H2 times H1 transpose, or H1 transpose times H2 transpose. Okay, and so again, what we did simply is we took the column vectors of A and we reflected them across a hyperplane. That again, we don't really care about this hyperplane. Just we reflected it across a hyperplane in such a way that the new vector lies along the coordinate axis, so that only one of its components is non-zero, and that is the norm of the old vector, and all other components are 0. Okay, if you have a vector in 2 dimensions, okay, that is x, y, and that is my vector here. Let's call it m. If you rotate it on the, reflect it on the x-axis, the first component will be the norm of this old vector, and the other one, so the y component, will be 0, because as said, this now lies on the x-axis. I hope it is clear. Yeah, you can of course also do the same thing with the y-axis, but we don't do it like that for the Householder transformation. You could, as said, you could reflect it in such a way that the vector m lies on the y-axis, not on the x-axis, so on the second component axis, not on the first one, and you would get something like that. That could be done, but we don't do it like that for the Householder transformation, but you could try if you want, okay? So in this case, the second component would be the norm of the old vector, and the first component would be 0, okay? And so again, just for information, if you forgot it, where does this vector u comes from? Well, if you look about it, this x prime is a set or reflection on the coordinate axis, and from x prime we can if we add the vector u from and the vector x prime together, we get our vector x. Okay, this is simply basic geometry. You have our vector here on the coordinate axis, so our reflection, and then if you add the vector u, we go to the vector x. Okay, here, and so we know that x prime plus u is equal to x, and so u is equal to x minus x prime, just for if you forgot it, where it comes from. Okay, yes, so I hope it was clear. So as usual, the hard part is probably to find this vector u, which is found from the first column vector, or the first column vector of the submatrix, or the first column vector of the submatrix, and so on. And then you find the vector x prime, which is the norm of this vector. Yes, and then you plug in everything into the formula. Remember that this u transpose u is simply the dot product of the vector u with itself. Then you plug in everything. I really advise you to use a calculator or a computer to do it if it's not in an exam, because in an exam generally the numbers are neat, but in real life this is mostly not the case. So yeah, use a calculator if you can, because it's really messy also, right? Yeah, so then you apply, you get your Householder transformations, you apply it to A, you get, yes, you get what you expected, so 0 elsewhere, and the norm of the old vector as the first component. And then you consider your submatrix, you do the same thing again, but this time the first column vector is the first column vector inside the submatrix. Again, you do the same thing, you find x prime, which is the norm of this first column vector inside the submatrix. You find your vector u, you find your Householder transformation inside the submatrix. Then again, you plug in these Householder transformations inside the matrix that has the original dimensions as your matrix A, and you plug in 1s in the diagonal and 0 elsewhere to fill in everything so that the dimensions match again with the dimensions of A. Okay, and yeah, then you proceed like that. You apply your second transformation, and you continue if you are in higher dimensions, and you do your calculations with A is equal to QR, so Q transpose is equal to blah blah blah, and that's it. Okay, I hope it was clear. And again, all we did basically is reflecting vectors. That's all we did. Yes, I think that's it. Thanks for watching.